Let's Make a Deal.
At first glance, Let's Make a Deal is a very simple TV show, but it brings in one surprisingly tricky scientific paradox. It was named after the show's host, the Monty Hall problem. The main game mechanism is that behind one of three doors, the creators hid a car. To get it, you just need to name the right door. Let's imagine you picked door number 1, but the host teases you and doesn't immediately announce the result. Instead, they open door number 2, and you see a goat standing behind it. Now, you're allowed to either stick with your initial choice or pick another door. And I'm 99% sure that if you make a decision without taking the Monty Hall problem into account, you'll lose and leave as a proud owner of the goat. But why? In this video, you'll learn much more than just tips for winning a car. I'll answer the following questions. How can you become your own grandfather without destroying the whole universe? Why does the color of our sky perplex astronomers? Who's watching us from inside black holes? And finally, what paradoxes keep scientists awake at night? Some paradoxes make our traditional logic hopelessly break down. If you take a good long look into the cloudless night sky, you can see around 800 stars. But only in our galaxy alone, there are approximately 400 billion of them. And when it comes to the infinite universe, this number is just countless. Then why doesn't the night sky shine brighter than the sun with all those stars? And even in the daytime, shouldn't the sun be lost among them like a headlamp among huge spotlights? This is called Olber's paradox. Astronomers of the 19th century felt almost miserable because of it. The person who discovered the paradox, Heinrich Olbers, assumed that cosmic dust blocks the light emitted by distant stars, but none of his colleagues was quite convinced. It was hard to believe that the universe had enough dust to dim down the super bright skies. In 1901, William Thomson proved this mathematically, although his calculations centered around the stationary universe. In other words, Olber's paradox works only in a world that doesn't expand. And among other things, this helps scientists establish that our universe is different. In the 30s, Edwin Hubble confirmed that the universe does expand, and the light coming from faraway sources disappears in the dark because of redshift. But don't let the romance of the night sky distract you. You're here to get that car, right? It's high time to analyze the Monty Hall problem and understand why you lost. Let me remind you that you picked door number 1, and then the host showed you a goat behind door number 2. This means the car could be behind the first and third doors with equal probability. In this situation, most people would think the big prize is probably really hidden behind door number 1, and the host is trying to mislead them. Besides, the chance of finding the car is not 1 in 3 anymore, it's 1 in 2. But the truth is, you'll almost certainly lose unless you change your initial decision. But why? Therein lies the paradox. When you picked the first door, you indeed had a 1 in 3 chance of finding a car on the other side. But as soon as the host opened the second door and you saw the goat, the probability of winning didn't increase, even though you were left with fewer options. Contrary to common logic, even if you stick with your original plan, your odds of getting the car stay the same, 1 in 3. Meanwhile, they double in relation to the remaining door, and now it's a 2 in 3 chance. It seems that the mathematical probability of winning as such is drawn to that very door, and the best advice here would be to switch your choice. Now, let's imagine that you lost anyway and got a very special hotel suite as a consolation prize. Welcome to Hilbert's Infinite Hotel. We have infinitely many rooms here, but unfortunately, all of them are occupied. How do we accommodate you? Don't worry, there's a way, and it's quite paradoxical. We'll just shift each guest to the immediate next room. The guest from room 1 will move to room 2. The guest from room 2 will move to room 3, etc. As a result, the first room is now free, and you can use it. The Infinite Hotel remains completely full, but can still keep welcoming one guest at a time. But what if the receptionist has to deal with not just one, but an infinite number of new arrivals? Common logic suggests that it's absolutely impossible to find vacant rooms for all of them. But the paradoxical manager of Hilbert's Hotel will laugh in its face. There's a very simple solution that will do the trick. The manager asks each existing guest to move into the room whose current number is twice that of their current room. As a result, all the even-numbered rooms are occupied and all the odd-numbered rooms are free. Moreover, there will never be a lack of them because we'll never run out of odd numbers, meaning that the infinite flow of new guests can stay with no trouble. And if some guest is rude and annoying, you can always give the brawler a key decorated with an infinity symbol and have fun watching their quest for the right room. However, some paradoxes not only defy our usual logic, but undermine the foundations of science. What paradoxical experiments put scientists in a deadlock? In 1927, physicists were racking their brains over the quirks of most ordinary light. In some tests, it acted as a stream of particles, photons, while the others proved it to be a plain wave. To finally find the reason, scientists began sending the light through a plate pierced by 2 slits. Their scientific logic told them that if the light was a stream of photons, each of them would leave 2 bands on the sensitive screen behind the slits. In case the light was a plane wave, it was supposed to form a smooth interference pattern some distance away from the slits. Can you imagine how surprised researchers were when they started detecting photon hits, not just in 2 places, but along the entire interference pattern produced by the wave? Instead of accurately determining the nature of light, they realized that light is both a particle and a wave simultaneously. But even that wasn't the strangest discovery. To find out what exactly makes photons cluster along the wave pattern, scientists installed photon detectors in the slits and ended up even more confused than they'd already been. That's because the traces they saw on the screen were 2 bands. This paradox was called the observer effect. It seemed photons felt that people were looking at them and started acting exclusively as particles. But as soon as scientists turned away, they continued moving along the waves. And not only photons were playing this game, electrons and even molecules were just as mischievous. The double-slit experiment was successfully repeated using fullerene composed of 60 atoms. All of them also acted as particles and waves simultaneously, and the observer effect prompted them to make a choice. Moreover, further double-slit experiments showed even more paradoxical results. It became clear that particles can decide what to do after passing through the slits. I mean, they send messages to themselves back through time. What can happen if we gain the same ability? I bet all of you would want to use the time machine to warn your younger self against making stupid mistakes. But in this case, you risk creating the bootstrap paradox. Let's imagine you're more interested in scientific progress than in your own day-to-day existence. So you decided to help young Einstein develop his theory of general relativity and change the world forever a bit sooner. You grab the articles written by older Einstein and deliver them to his younger version, and he eagerly gets them published in a scientific journal. But who is a legitimate author of those works now? Not young Einstein for sure, because he didn't write a single word. And not you either, because you just printed out the text. Congratulations, you guys are trapped in a causal loop. Well, the theory of relativity basically appeared out of nowhere. And what if someone tries to meddle in their family's past? Imagine that you went back in time to revisit old places from your childhood. And nostalgia hit so hard that you decided to drown your sorrows in a local bar and got into a fight. As it spiraled out of control, you accidentally killed a man that had looked very familiar from the very start. No way. That was your young grandpa. And now you have to face both problems with the law and the grandfather paradox. If you killed him before he met your grandmother, you could never be born. Consequently, you couldn't travel in time. But then who killed Grandpa? I guess you feel like the entire universe is just about to explode together with your brain. Even the most innocent idea of helping Einstein leaves questions. If you handed him the finished research and sped up the breakthrough, what motivated your future self to go back in time? Because of such obvious causality violations, Einstein himself considered time travel simply impossible. Or maybe someone told him that. Other scientists, however, insist that there are still ways to dodge through time paradoxes. The multiverse theory states that when traveling into the past, you create an offshoot of your own universe and are free to do anything you want there. Kill your grandparents, make friends with Einstein, and boost the development of science, but you'll never return to your home world. Although even within one timeline, there's an unexpected way out. In 2020, a journal called Classical and Quantum Gravity published an article that will definitely be approved by all temporal grandpa killers. It was written by Germain Tobar, who created a revolutionary mathematical model of time and causality. To illustrate it, the author used an unusual round pool table. If you push balls, they'll first chaotically bang around the table, but once they start hitting each other, all of them will eventually return to their original position without problems. If we draw an analogy, an attempt to kill your grandfather in the past is a hit, and then, according to Tobar's model, one of two things will happen. Your fist or gun will miss the target and never hurt him, whatever you try, so that he'll anyway live on as he was supposed to. In the case of aiding Einstein, you may be struck by lightning when delivering the printed papers, meaning that the theory of relativity will be burned to ashes, and no time intervention will occur. The other scenario suggests that even if you reach Einstein unharmed, for various reasons, the theory of relativity won't be published before the due date, and the universal balance will be maintained. And even if you make an extra effort and finally get your old man killed, you'll meet a pretty girl and stay in the past to be with her. Spoiler alert, this is your grandma, so you become your own grandfather. Isn't it awful? It's not my fault, nor Tobar's either. Blame the universe that will protect the usual course of events and causality at all costs. But it's even more interesting to learn why we are all able to appear on this earth with this exact sun in the sky. Even after Olber's paradox was solved, stars still have a lot of other enigmas in stock. In 1958, Martin Schwarzschild and Fred Hoyle came to an unexpected conclusion about our sun. Everyone knows that as time goes by, it becomes increasingly hotter. But this also means it used to be much colder in the distant past. According to the most accurate estimations, 4.5 billion years ago, the sun generated 30% less heat, meaning that the average temperature on our planet's surface could be about -7 degrees Celsius, and that would freeze all primordial oceans. But wait, don't we know everything was the other way around? The oceans were liquid, and this state sparked life on Earth and the beginning of humankind. It's called the faint young sun paradox, and it's been haunting astronomers for over half a century. In 1972, Carl Sagan and George Mullen tried to solve it by assuming that Earth used to have a denser atmosphere full of ammonia that retained more heat due to the greenhouse effect. It sounds very plausible, but chemists later discovered that the sun's ultraviolet radiation would have destroyed ammonia. In 1981, experts came up with a volcanic solution to the paradox. They suggested that young Earth was heated up by eruptions that also released quite a lot of carbon dioxide into the atmosphere, triggering a strong greenhouse effect. Finally, there's a version that the temperature of young Earth spiked after colliding with planet Theia, and as a bonus, this crash gave us the moon. But ultimately, none of the possible answers fully explains the paradox, as the sun was young for a pretty long time, and the heat it couldn't provide had to be somehow compensated. Could our descendants invent a time machine and take a trip to the past to install a small nuclear reactor in the Earth's core? If so, I'm afraid we're all stuck in one big time loop, and I have no idea where we came from. But that's not the only sun-related oddity. All modern knowledge of space indicates that the sky above our heads is the wrong color. It looks blue because part of the sunlight scatters in the atmosphere in a special way. Though paradoxically, the sky is supposed to be red, all because the sun isn't the best star we could get for sustaining life. This yellow dwarf can last only some pathetic 10 billion years. Meanwhile, 75% of stars in our galaxy are red dwarfs, able to keep shining for trillions of years. So why, contrary to the probability theory, haven't we been born on some of the planets orbiting one of those stars? Especially since astronomers now find more and more Earth-like exoplanets around red dwarfs. Trying to resolve the red sky paradox, astronomer David Kipping surmised that red dwarfs aren't as perfect for sustaining life as everyone tends to think. After all, a planet must move closer to a colder star to preserve liquid water on the surface. Compared to the extreme outbursts red dwarfs are prone to, solar flares look like harmless puffs. Those outbursts can sterilize a whole planet and even strip away its atmosphere. That's why the sky on the most theoretically life-friendly planets near red dwarfs is probably not even red, but black and radioactive. But arguing about the color of the sky doesn't seem so important once you realize dozens of thousands of stars are missing up above. It seems that you'll find billions of galaxies whatever corner of space you peek into, so none of the astronomers is ever going to be redundant. And yet, they're on the brink of panic because they don't see enough dwarf satellite galaxies. If you live in the northern hemisphere, you can easily spot two of such little companions of the Milky Way, the large and the small Magellanic Clouds. But in truth, our galaxy features 59 satellite galaxies orbiting it, and all would be fine, but old models recreating galaxy formation evolution, including even the latest and smartest of them, like a computer simulation called ERAS, which tells astronomers that there must be more dwarf galaxies. According to these estimations, the Milky Way is supposed to have from 10 to 100 times more satellites. Well, where are they? This paradox was dubbed the dwarf galaxy problem, which drives astronomers crazy. Where's the mistake? Are the super accurate computer simulations wrong? Or are there dozens or perhaps hundreds of invisible worlds with innumerable stars lurking somewhere in outer space? And which of these possibilities is worse? In 2004, Beth Willman, a researcher from New York University, accidentally noticed a possible explanation when she looked at her colleague's computer screen. There was a strange dim spot that further studies identified as a completely new object, an ultra-faint dwarf galaxy. These things might be everywhere, and we don't see them only because our telescopes aren't good enough. And if we can't detect entire galaxies, there's no need to guess why we've never met their residents. Where are all the aliens? That was the exact question that physicist Enrico Fermi once asked his colleagues, and thus devised the famous Fermi paradox. It's a good question if you think about it. Our universe is composed of billions of galaxies and trillions of stars. So how come we've never found any traces of other civilizations? Physicists hoped that when engineers made more powerful space telescopes, we'd be able, if not to meet our space neighbors, then at least receive their radio signals. However, we've spent decades scanning all possible frequencies in different regions of the sky within the SETI project and heard only silence in response. Good scientists have simply picked a bad time or the wrong place to listen to. After all, space is enormous, and the chance of intercepting messages sent through the galaxy is much lower than overhearing someone's telephone conversation in a desert. Desperate to solve the Fermi paradox in 1960, astronomer Frank Drake proposed an equation that lets us estimate at least an approximate number of civilizations able to transmit signals within the Milky Way. Drake included a lot of various parameters into the equation. How many stars have planets similar to ours? How many of them are suitable for life? And how actually likely is life to develop on them? He also didn't forget to add the likelihood of the emergence of a technological civilization ready to contact us and equipped with powerful transmitters. With the help of the Drake equation, scientists concluded that right now there might be from 50 to 50 million such civilizations in the Milky Way. These results are quite controversial, but one thing is crucial here. From a mathematical perspective, there must be enough aliens to be detected by humans. Of course, unless there's some error in the Drake equation. What do we really know about the probability of life arising on an Earth-like planet? It seems some of the trillions of worlds are bound to be habitable, although in fact, we have only one example right here, and even it isn't studied sufficiently. Biologists Peter Ward and Donald Brownlee are sure that we gravely underestimate the uniqueness of life on Earth. Their rare Earth hypothesis states that our planet developed pretty specific conditions and, as a result, a remarkably stable ecosystem. It has enough liquid water and oxygen. Earth's axial tilt makes seasonal transitions smooth, while the ozone layer blocks the deadly ultraviolet radiation from the sun, and gas giants like Jupiter and Saturn shield us from the majority of dangerous asteroids. I've mentioned just a few of probably thousands and millions of factors that let us live and go on wondering, hey, where is everybody? But isn't the answer obvious? All other civilizations never came into being and never had a chance to send any signals because their own planets could never give them exceptional Earth-like conditions and therefore any future. But if there's something scarier than cosmic loneliness, that would be living near something unknown in complete silence. In his novel titled The Black Forest, Chinese author Liu Cixin suggests the most terrifying explanation for why we can't find any traces of other civilizations. According to his version, there may be even 50 million alien races in the Milky Way alone, but all of them are hiding in fear because they suspect that contacting strangers will entail not peaceful discussions of space paradoxes, but rather the extinction of one of the parties. This is exactly why forest creatures on Earth prefer to lay low in the grass at night to avoid getting noticed by other animals. Even if the possible threat turns out to be just a mouse and not a hungry wolf, it's still much wiser to play it safe and, in case of detecting any sort of movement, strike first. Liu Cixin believes that for this very reason, all civilizations in the universe consider each other potential enemies and prefer to keep quiet in this dark and wild forest. It seems we're the only society that ignores the rules of survival and stubbornly continues to send signals into space and thoughtlessly give away our location. So when should we expect the attack? We can only hope that this solution to the Fermi paradox is wrong. But what if the truth is truly shocking? What if I tell you that aliens have already been here? If at least one of the technological civilizations managed to build starships traveling faster than light, it gets a chance to reach not only any corner of the universe, but also go back to the point of its past. It follows from Einstein's theory of relativity, where breaking the speed of light creates the possibility to kind of turn back time. Moreover, Earth's history repeatedly mentions events that look very like alien encounters and even images of spaceships. It sounds like science fiction, but Carl Sagan and other respected astronomers took the paleocontact hypothesis very seriously until the History Channel made a complete mockery of it. However, the most unexpected assumption in this story is that aliens are us. The directed panspermia hypothesis neutralizes many contradictions around the Fermi paradox. But what if Earth got all these unique conditions, not accidentally, but as a result of deliberate terraforming in the distant past? What if we're just a colony of human-like species that survived a certain cataclysm and forgot how to assemble devices needed to communicate with the metropolis? Maybe it's not a transmitter at all. Perhaps it's neutrino and gravitational wave generators. And at the same time, nobody bothers to send us help because these resources are more helpful if used to explore new planets in space-time. So, if you happen to get in touch with your great-grandpa who lived ages ago near a red dwarf, don't forget to ask him how he coped with its violent outbursts and managed to colonize Earth. But some scientists are sure that not only humans are watching the universe, but the universe is spying on us as well. And I'm not talking about aliens now. Astrophysicists Dane Danielson, Gautam Satish Chandran, and Robert Wald put forward a paradoxical hypothesis that black holes can literally be the eyes of the universe. They suck up light from all across space and this way collect information about it. Researchers have long been struggling to understand what exactly is happening out there, since the black hole information paradox sort of deletes their contents from the universe, which is simply impossible from the perspective of quantum mechanics. But a new hypothesis says that this information doesn't disappear and actually performs essential work. Remember those photons that decided to act like particles only when closely monitored? Well, according to Danielson and Company, black holes serve as observers of the universe that force it to take a strictly defining shape and save it from collapsing into quantum chaos. This means space is full of dead black eyes that, on the other hand, guarantee our safety and well-being. Isn't it clearly paradoxical? Leave a comment and tell me which confusing facts surprised you the most. And do you think you would win in GOAT?